My name is Jamie Wahlin. I'm a software engineer at TCN, and today I will be speaking about connecting applications with Protobuf and Bazel. First off, I want to introduce TCN. TCN is a leading provider of cloud-based call center technology. Our products include inbound, outbound, speech IVR reporting, and workforce optimization features. We're based in the unlikely location of St. George, Utah. It's just an hour away from Zion National Park, which is pictured here. And yes, I have done that hike. It's terrifying, but I highly recommend it. TCN started out with a monorepo in 1999. We had a small team, a rapid development cycle, and the monorepo worked wonderfully for us for a few years. Our code base grew, and we started facing complicated dependency management issues, long build times, and out-of-memory errors, which forced us to migrate to multiple repositories. In 2016, we adopted Protobuf and gRPC for the 4th version of our product. As our number of repositories has multiplied over the past couple of years, and our number of languages has increased, it has become increasingly difficult to manage our protos. These are some of the challenges our team has faced. We found it difficult to keep applications in sync. For example, if a developer updates a protofile in one repository and there are 10 others that depend on it, they have to update those 10 other repositories, and if they forget, which they would sometimes, there would be unexpected failures. We dealt with mismatched proto bindings. We didn't generate any front-end proto bindings. We struggled with multi-language compatibility issues in our protos, and the files were scattered across multiple repositories, so it was time-consuming to track down our contracts and expectations. These challenges were negatively impacting our development velocity and needed to be addressed. At the beginning of this year, a few team members and I investigated Bazel and began to transition to it. We started off by migrating individual repositories to Bazel. This included generating proto bindings with gRPC using Bazel's existing rules and also their custom rules, which we needed for our 2 in-house Proto-C plugins. Just as a side note, these 2 plugins are really cool. One generates a persistence layer for Go from a proto file. This one's open source. There's a link at the end of the slides if you want to check it out. And the second generates a Redux state from a proto file, effectively bridging the gap between protos and our application state. Next, we consolidated our proto files into their own repository. This was made possible by Bazel's ability to generate proto bindings from multiple languages and by its caching mechanism. Next, we ensured that our front-end applications remained in sync with our protos. In order to do this, we adopted TypeScript and utilized 2 of Improbable's open source tools, namely Proto-C GenTS and gRPC Web. We were able to reliably generate these proto bindings for TypeScript because of Bazel's standardized sandbox environment. We now benefit from compile time errors if our front-end applications are not in sync with our protos. Next, we moved to the monorepo, went back to our roots. This was made possible by Bazel's fast builds, remote caching, and support for all the languages in our stack. We faced several challenges along the way. We discovered there was a big learning curve initially. Some rules were not mature at the time we needed them, and our team had to sometimes forcefully adjust to new tools and development processes. We even had a SAS controller that melted. That was exciting. And this was on the machine that was running all of our CI builds. We think it was due to too much I/O, so we've limited the number of cores each Bazel build can use, and so far so good. Now, think back to the challenges our team faced with the protos. Bazel helped us directly or indirectly tackle all of these challenges. We now generate proto bindings for every language in our stack without complicated scripts. We've consolidated all our proto files into a single directory so we know exactly where to look for contracts and expectations. And we've transitioned to a monorepo, which has synchronized our applications and streamlined the generation of proto bindings. Overall, Bazel has made it easier for our team to connect applications with protocol buffers. Thank you very much.
Hi everyone, I'm Jin. I work on the Android rules in Bazel, and today I'll be giving a status and overview of the Android rules in Bazel. So what's available now? What you can actually use now? The Android rules. To integrate with the Android SDK and NDK, there are repository rules. Oh, by the way, these are all native. These are all built into Bazel. To build apps, you have the Android binary and the Android library rule. To import Android ARs, you have the Android AAR import rule. To run emulator and device tests, you have the Android instrumentation tests. To run roboelectric tests, you have the Android local tests. And then to build cache emulator images, you have the Android device rule. It's fully integrated with Android Studio. The plugin was released open source 2 years ago, and this works on Windows, Mac, and Linux. So as a summary, this is the complete matrix of what we support right now, and with the exception of Android implementation test, device, and building apps on RBE, everything is supported on all 3 OSs. So performance, we have been doing a lot of work on performance recently, and we discovered we have addressed bottlenecks and achieved up to like 2.5 times speed up in the Android resource processing pipeline using persistent workers. We also improved things like DEXing, workers for DEXing, integrating with APD2, and decoupling the Android resourcing processing pipeline. And so we achieved quite a fair bit of improvements here. So there's a Bazel command called Bazel Mobile Install. This is an alternative to Bazel build and then ADB installing your app. So this gives you this fast iterative development workflow. And internally we have benchmarks, and the rate one is mobile install. It's a lot faster essentially. So the Android rules feature Java 8 desugaring, which allows you to use Java 8 language features like lambdas, and Java 8 libraries like streams on Android. There's a blog post by Kevin Bierhoff. You can check this out for more information. We have heard a lot about remote build execution today, and I'm happy to share that Android builds do work on RBE as well. Yeah, and on the right you can see the new JSON profile generated from Bazel, created by Tobias. And I think, yeah, and this is actually in Chrome Tracer. So you can actually see the full trace of your build in Chrome. Kotlin rules. The community has created rules for Kotlin, for building Kotlin, and they recently added support for building Kotlin for Android using the KT Android library rule, and this is available in the rules Kotlin repository. What we're working on right now, we are actively migrating the rules out of the Bazel server into Starlark. This recouples the release cadence, and it reduces the Bazel size. It's available in rules Android. Mobile install v2, we are actively rewriting mobile install into Starlark. This is into a faster, more incremental version of it, and it works with APD2. More work on performance improvements. We are trying to come out with a benchmarking framework for tracking Bazel's Android build performance over time. Emulator testing on RBE. This is a big one, because right now, if you want to launch 9 emulators on a local machine, you need a very beefy machine. If we can do that on RBE, that would be amazing, like 100 emulators at the same time, with minimal configuration, so no changes to existing build. Future work. We want to improve our dependency management. Right now it's a bit manual, so on that. Migration support. We want to create tooling guidance and documentation for moving Android builds to Bazel. Faster Android Studio plugin releases. We are going to refresh our rules into, for example, we want to support dynamic apps using the Android module rule. We want to split up building of the build logic into Android application, Android library. And finally, we want to also contribute more to the Kotlin rules. That's it. If you have any questions, feel free to approach me or my TL Alex at the back. That's it. Thank you.
Hello everyone, my name is Irina and I work in Bazel team. Let's speak about C++ project which uses Bazel as the build system. Very probably that project will use some third-party libraries, and very probably those third-party libraries will not use Bazel, but will use some other build systems such as CMake or ConfigureMake. The question is, how can we build such project? One way would be actually bring those third-party libraries to Bazel. This requires reverse engineering of the existing build scripts, which is a non-trivial task, takes time and doesn't scale well with many libraries. The other way is to actually run the builds of those external systems as part of our build and bring results to Bazel. If you create a rule for each external system, then all the complexity of dealing with it would be inside the rule. And so the work for bringing each dependency in our project would be minimal. This scales well and gives user the choice of gradual adoption of Bazel. This is what Bazel team is working on now. This is a GitHub project, of course in Starlark. So let's have a look at the example, how it can look in the build file. Let's say we have CMake external rule, which we supply with the sources and dependencies, and then we can pass that target into the CC library or CC binary. Some design highlights. Since there are so many other build systems in the world, we do not want to build individual rules, but we want to create it as a Starlark framework, easily expandable. We modeled the build of the libraries as a black box with both configure and execute steps inside one Bazel action. As it is the normal Bazel action, we would benefit from caching, and since you do not change the versions of your libraries that often, the cache values is going to live relatively long. We want the user to have the full control over the external build. That's why we provide the possibility to pass any options to the external system and also add some parts to the underlying shell script. Our rules should interoperate with Bazel, read Bazel settings and C++ toolchain, so that the user doesn't have to define the same things 2 times. And we also need to access C++ information of our dependencies and provide such information. The good news is it is already available in Starlark in Bazel 0.17. We already have CMake rule ready, and we are working on auto tools and ConfigureMake. Our next plans also include remote execution support. This is our GitHub repository. We would be happy for your feedback and contribution. Thank you.
Hello, I'm wait. The speaker notes are. I'm going to be speaking to you about why to use Rules Kubernetes and Rules Docker to deploy your Bazel applications to Kubernetes, and how it works to give you fast, correct deploys. I'm also going to offer 5 general Kubernetes with Bazel tips, all in 5 minutes. Kubernetes is smart enough to deploy only what you change, and it does so by hashing its inputs, just like Bazel. These hashes include both the YAML and the exact versions of the containers that you're running. Taking advantage of incremental deployment in Kubernetes requires that you can deterministically generate all of your inputs, including your containers. Rules Docker provides rules for generating container images deterministically, allowing you to build a single, repeatable package from base container to your own application code. Rules Kubernetes builds on this. It takes as input a set of Docker containers and an input Kubernetes YAML with container reference placeholders. It builds your containers, pushes them to the container registry, gets the SHA-256 of each container image, and then replaces those placeholders with the resolved SHA-256 references. This approach really shines with a multi-application monorepo. When you change shared libraries, Debian files, tooling, etc., you need to know which components need to be deployed. In a simple application, you might be able to keep this in your head. At scale, you need automation. With this approach, we avoid two problems: under-deploying, not deploying change components, leaving them unvalidated on master, and over-deploying, waiting for potentially expensive rollouts despite not having made changes. We can radically simplify our CI/CD flow. We can have a single pipeline for building, testing, and redeploying all of our applications, relying on Bazel to negotiate what actually needs to be deployed with the container registry in Kubernetes. In order to understand how to take advantage of what Bazel gives us, it's worth diving into how it works at a low level. How does Bazel negotiate this reconciliation with the container registry in Kubernetes? So just what is a Docker container? It's an ordered list of tarballs representing file system changes, additions, edits, and deletions. Each layer is represented as a SHA-256 of the uncompressed contents. The overall image is a SHA-256 of the layers and the metadata. Rules Docker builds these layers with Starlark and Python. Not having to run the Docker client or the daemon simplifies build in CI, removes the issues with building Docker images from within a container, and allows Bazel's parallelism to speed container layer building. The standard container registry v2 API provides caching from the local build to the remote container registry. Rules Docker uses HTTP head requests to check for an existing SHA-256 of an already cached container image and the SHA-256 of each container layer. Finally, Kubernetes deployment hashes the pod template to determine if your application needs to be redeployed. If the pod template hash is unchanged, there's no need for a rollout. And with this, you have the benefits of Bazel's repeatability from source to deployment. And now for the tips. Many Kubernetes applications don't need a full operating system and can simply package up their direct and runtime dependencies. For Java, that's glibc, SSL, and the JVM. The distrolist project provides simple base image, and Rules Docker provides rules to utilize them. But sometimes you do need a full operating system and a package manager. In that case, the aggregate Debian package rules from Bazel toolchains provides transitive Debian package resolution in a deterministic Bazel-friendly way. There are many Kubernetes workflow tools besides Rules Kubernetes. Whichever one you use, prefer SHA-256 references for first-party code. This is supported by default in Scaffold, for example. And most of them will still allow you to build your Docker images via Rules Docker. Most Kubernetes users will eventually face the wall of YAML problem, how to tame thousands of lines of configuration. Instead, consider using the Kubernetes client APIs rather than YAML for complex applications. You get IntelliSense, compiler support, and other first-class language tools lacking in YAML. The Pulumi project is a bit of an inspiration here. It allows you to create cloud resources, projects, clusters, buckets, etc., and Kubernetes objects with real programming languages, not DSLs. It's a refreshing alternative to YAML and other limited configuration languages. And finally, if you're using Docker and Kubernetes, you may also be using Grafana for graphing. My colleague at Etsy, Kevin Gessner, has written Bazel rules for creating parameterizable Grafana dashboards with Python and installing them in a Docker container running a properly configured Grafana. Thank you for coming, and please contact me at the conference if you have any questions.
Hi, I am Laurent. I have been working on Starlark. So Starlark is the language you use for writing build and Bazel files. And I will give you an update. So what we've been working on about the language and mostly about the tooling. So, so if you've ever heard the name Skylark, just forget about it. It's called Starlark. Okay? So we've been working on trying to simplify the build API. So the big focus was on simplifying the rules and making them simpler to use, and so simplify the API. And the real goal is to make sure that everything is stable. So every function should be properly documented with nice examples, easy to use, or we should remove it. So we are not there yet, but so we're working on it, and the real focus is to get stability before Bazel 1.0. So this is just a list of things we've been working on. For example, the first one, ctx.actions.args. So if you write Starlark rules, you might want to use it. It will allow you to create more efficient command lines. Data configuration has been removed, so that's also a nice simplification if you've seen that before. And a few other things. And we have also a separate repository for Starlark with a complete language specification. We have also been working on a lot of tools. So one of them is Buildifier. So it has been around for some time, but it can now format BCL files. So this is production ready. We are using it at Google. We have reformatted all our 50,000 BCL files, and it's used as a pre-submit check, so it's working. On top of that, we have a bulldozer. So there are not many news on this front. It's just that, so if you want to edit your build files automatically, so either you have lots of them or you want to use that from a script, you can add or remove dependencies easily with the command line interface. You can also use a Go API if you want to do more complex code transformation, like rename a variable across the entire code base, or these kind of things. This is also production ready. We have been working on a linter. So we already had a linter, so we are working on a replacement. The code has been submitted today. You can try it. It might work, or maybe soon. And so, so having a linter is nice, but most of the time you don't want to manually read all the warnings and fix them yourself. So we are providing a new command, so with Buildifier to automatically apply fixes to your build and BZL files. And this is important as we're making changes to Bazel, so incompatible changes, and you want to keep your code working with Bazel. So also this has been submitted today. We are going to work on it. Contributions are welcome because we can add more automated fixes. We have been working also on documentation generation. So there was a tool called KaiDoc. It was not working well, so there's a replacement that is coming soon, like in the next few months. That should make things much easier for people who write Starlark rules and want to provide good documentation for your users. And we have a debugger. So typically when you have complex code, you want to, you might want to debug it and have a breakpoint and execute line by line. So when you have complex Starlark code, you will be able to use a debugger. So there's a VS Code plugin that will be submitted in the next few months as well, and IntelliJ that's also soon. And finally, in any IDE, what you really want is code completion. Like you start your writing your BZL file, and you want to see what functions are available. And code completion is here in more details.
Hi, everyone. This is Andreea. Thanks, Laurent, for introducing my project. I've been working in the Bazel team for the last 4 months, and I've been working on integrating Starlark in an IDE, all those nice features that can speed up your coding process. So first and foremost, the project is not yet open source. The plan is to release it at the beginning of next year. So you can soon try out and see for yourself how all the features work. Okay, so when I say all the features, I mean the following four. I mean code completion, go to definition, signature help, and diagnostics. All those four features are implemented in a language server, which means that it has behind it the language server protocol, which means that you can plug it in any IDE that supports it. So you can have same features and same implementation in VS Code, in Eclipse, in Vim, in Emacs, and a few others. So first and foremost, it's code completion. So that was the first feature that I implemented. And I think the coolest thing about it is that, you know, in a language like Starlark, which is new and not yet widely known, I think it's way easier to learn it because it gives you nice suggestions, it gives you relevant suggestions, it gives you context-aware suggestions. And for example, you have all the loaded symbols, you have function names, parameter names, everything that you declare inside a file, and also all the build-ins. And I think it's pretty nice to have the build-ins because, you know, you don't have to go back and forth between your IDE and the specs and the syntax and the documentation. You have everything there. So you have in context actions, you don't need to know that there are 3 functions. You know it because it's there. So you know the name, you know the required parameter, the return type, and also the official documentation. And then what we're doing is that we're trying to kind of improve the completion with some type inference. And we base this on some cases. And the first one, it's we look at var. And by looking at the right-hand side, we know that it's a string. And then knowing that var is a string, then we can understand that the greeting is a string too. So then knowing that greeting is a string, then we can actually give you suggestions that are relevant. So all the built-in functions for string. Then this is a nice one. What we're doing, we're basing this on the assumption that programmers are decent and they follow conventions. So what we're doing is that we're looking at the doc strings, and in this case, we can understand that the parameter CFG is of type configuration, just because you specify that. Then we have path completion, and I mentioned that we have relevant suggestions. So when you're inside a load path, we actually give you suggestions for paths that you can load. And then once you have the loaded path, then we give you suggestions for symbols that you can load from that path. And the next one, it's go to definition. And you know, it's pretty nice to just jump around in the file and see where was this defined in the global scope or inside the function body. But I think the nicest use case is when you load something, and when you use it, it actually jumps to the definition. So opens the file and places your cursor where it's defined, so you know what you're using. And then it's signature help. And signature help is this text box that you have behind, above your cursor when you're inside a function call, and just tells you the many parameters that you have to fill in when you call the function. And the last one, it's diagnostics. And the diagnostics are the result of calling bulldozer. And what we're doing is just to render all the warnings and all the errors in the UI so you can just catch them early. Yeah, that's been my intern project. Oh, those are all the features that will soon be available, so just check it out and make sure you're trying once they're out there. Yeah.
Hi, everyone. My name is Jodi. So in my experience, making developer feedback loops shorter is win-win. It makes your code better, and it makes you happier. So why don't existing commercially available CI tools go further to give you high-quality feedback faster? The project I'm going to show you today is my sketch of the ideal CI. I had 2 goals in mind. First of all, I want to give you feedback as fast as possible. The feedback should be fast enough so that you can stay in flow while writing code and not have to do any context switching. Second, I want to give you better feedback. For example, I could tell you before you push to the upstream whether or not your changes will integrate with it. I could also tell you before you push to the upstream how much of an impact your changes are going to have on the system. I decided to build a CI specific to Bazel rather than supporting many build tools because I think it will provide a better developer experience. Bazel speed is, of course, the foundation for fast feedback, and its extensibility makes CI for multi-language systems simpler. But perhaps most importantly, Bazel gives me access to the abstract graph structure of the build, which allows me to provide much better feedback than would otherwise be possible. Okay, enough introduction. Now let's take a look at what the project actually does. It consists of a command line client that you run locally and a remote server that's private to you. Every few seconds, the client detects any changes that you've made locally that you haven't yet pushed to the upstream, and it sends those to the remote server. On receiving those changes, the remote server first pulls from the upstream and builds it. If the build succeeds, your local changes are integrated into the upstream using a rebase, and finally a build is run on the integrated code. Feedback about the process is continuously communicated to you so that you'll find out immediately if there's any problem, like that the upstream doesn't build or that there's a merge conflict. At the end of the loop, you'll know that your changes are good to push to the upstream. Now let's take a look at the UI in a little bit more detail. At the top, I'm showing the current status. Here, I show you how many files you've changed locally. Here, how many targets directly include your changes. Here, I'm showing you the number of targets that are downstream of the targets that are directly including your changes. And this gives you some idea of how much impact the changes are going to have on the system. Here, I'm showing you the number of targets that are leaf targets that are downstream, and those are the ones that get passed to Bazel test. Below the information about the timing of the build, I'm showing you information about the success so far, which includes how many targets have been built successfully and how many tests passed. At the bottom of the screen, we show the Bazel logs. Now let's look at the project in action again. Again, the idea is that this tool is running continuously in the background, automating the process of pulling from the upstream, integrating your changes and building, so that as soon as you are ready to receive feedback about your changes, the feedback is already ready for you. You can stay in flow while writing code and still get great quality feedback about your changes. Right now, this is just a small prototype, but I can think of lots of interesting ways it could be extended. For example, I could let you know if someone else is editing the same files that you're editing before either of you is pushed to the upstream. If you haven't pushed to the upstream for a while, I could give you a reminder to do that to share your changes. I can also give you more information about the risk of the changes that you're making. For example, if a file that you're editing has a history of breaking the build. I'd also like to give you even faster feedback. For example, I could run the tests that are most likely to break first. I can let you know information about which parts of the build are running slow so that you can optimize them. I can also let you know even about tests that aren't providing any value because historically they've never found any bugs. That's all that I have time to talk about right now, but if any of you are interested in these kind of ideas, I'd really love to talk about it further. Please find me around the conference or drop me a line. Thank you.
Hi again. So what I'd like to talk about today, just on this very short talk, I'll try to be brief, is Bazel. You've heard a lot since this morning. It talks a lot about fast and correct. Let's accept fast, but I want to challenge correct. First of all, I want to challenge correct, and secondly, Melody this morning talked about the fact that at Google there were 2 billion lines of code in this in the biggest mono repo, and so something that's really important when you have 2 billion lines of code, and it's important for us too, even though we don't have nearly that amount of code, is to really never rebuild the world. And so I want to talk about how we at Twig use Bazel and try to achieve full correctness without rebuilding the world. so how do we get correctness? Actually, a big part of correctness is reproducible builds. And to get reproducible builds, you basically need two really key ingredients. You need your builds to be hermetic, and you need your builds to be deterministic. And so if you have hermetic and deterministic, those two properties together, then you can hope to get reproducible builds. The problem is that I don't think you really quite get reproducible builds with Bazel alone, because arguably Bazel builds are not all that hermetic. There's plenty of hermeticity holes in Bazel today, at least if you use it out of the box in the open source version, and I don't know how Google uses it internally. But out of the box, so for example, if you're using the C++ rules, or many of the native rules are basically auto-configuring the tool chains, for example, GCC, the C compiler, from the environment. And so if from the host, and if the environment changes, what happens then? Likewise, your builds will depend on a bunch of system libraries like glibc, libpthread, et cetera, et cetera. And also, in practice, a lot of the rules that are implemented in Starlark, they often use the run shell action. Sometimes so there's an option that you can pass to run shell that basically says, don't wipe the environment. So for example, I can call basically from that action any binary that happens to be on the path. So that's hurting hermeticity. There's a bunch of workspace rules that can also hurt hermeticity. So, the typical solution that people have to all this is, does Docker help? And the problem with Docker is that the build inputs are still not completely captured by the build description. I challenge you, in particular, to think about what happens if you change the Docker file that characterizes the image that you use to run all your actions in. Those changes, that can change completely independently of Bazel, and Bazel doesn't know when those changes happen. So you can get reproducibility problems there. The other problem is that Docker images are not always reproducible. And this is a known problem from a Docker file. And Docker images don't really compose well. Ultimately, there are no fine-grained dependencies in Docker layers. And so this means that as said in the beginning, you either have a choice. You can either somehow track the changes in the Docker files, but then anytime anything changes in the Docker file, you have to rebuild the entire world, right? Because anything in Bazel can depend on anything from your environment, from the environment provided by the Docker file. Or you can just say, all right, too bad. Forget about hermeticity. So I want to. So what we do at Twig is that we actually use another system, different from Docker, but very similar, which has the same ideas as Docker. So for example, you have a notion of derivation, which is essentially akin to Docker layers. But the difference is that derivations are much more fine-grained. We have a notion of expressions, which are kind of like Docker files. But what's the key there is determinism and reproducibility. And so because we have fine-grained dependencies, you can get targets in Bazel depend on specific layers in Docker parlance or specific Nix derivations rather than just the whole image. And so what this ultimately means is that your rebuilds, whenever you add a derivation, for example, your rebuilds are basically pretty minimal. So for example, if I just change zlib, then anything that depends on zlib will rebuild, but nothing else. So Nix is pretty cool. And so we added, we have an experimental rule set called rules nixpkgs that you guys can use. We often use, when we use Bazel in production, we nearly always use it together with rules nixpkgs. Thank you for your time.
Okay, so I'm Klaus Aehlig, and I'm talking about Bazel and external repositories. And by external repositories, the main interest is sources of truly third-party dependencies. And more precisely, I'm talking about the question which versions of these external dependencies you get. That all started with a discussion at last year's BazelCon, and there was kind of in some, well, discussion on, there was a vision that roughly looked as follows. So imagine you take a project, do a fresh checkout, and you look at the workspace file, and it's very declarative. It shows you which repositories to depend on, which are the relevant branches, and what transformations to do, and so on. But there are no specific versions. So it's abstract description of what are your external source dependencies. And that is something that has to be changed very rarely, only if you add a new dependency or remove one. And then you build, and you build at the latest known good snapshot. And then you check out an old version of your project, and you build against the version of your dependencies that were used at that time. So how did we imagine that even to work? We weren't thinking about Bazel doing some magic, but basically the idea was ignore the workspace file and use another file. And don't worry, you don't have to write that file by hand. It's generated from the workspace file in a controlled way, and it's get committed. So it contains the precise IDs, commit IDs instead of branches, and for a good measure also timestamps so that it can shallow clone. And it contains the hashes of the sources that you generated. So even with all your transformations and maybe not having the same version of these tools doing the transformations, you know that you have the right code, or at least you get notified if you did something wrong. And actually, it's just a Starlark value contained in that file, so the build can just load that file and do whatever it wants with these values, like adding precise snapshots of your dependency in the version string in a functional way. Okay, so the idea is you have a file that contains all the relevant information of the versions. And how would you think of updating that? The idea is to have a new command, Bazel sync. And then it looks roughly like that. You see some information saying, oh, I was executing the rule Google Protobuf, and this is the commit I get, and that was a timestamp and so on. So it executes the workspace file unconditionally, fully. It executes all the rules in the workspace file and sees what comes out. And it records all the version that the rules return, as this is a precise version I got when following the branch master in a file. And the idea is then to test and commit that file to the repository. And since that file is not just a Starlark value, but a nicely canonically formatted Starlark value, you also get meaningful diffs. And the good thing is that is reality now. Well, as of Bazel 0.19, but you can already download the first RC. But don't worry, we haven't changed the evaluation mechanism of Bazel completely. It's fully opt-in, controlled by the RC file. So it just need to add some options. It looks more scary than it actually is. So there's one option telling Bazel, well, whenever you execute an external a workspace rule, record the return value and the fact that you executed the rule in a file, and you name the file. So that is what you want to do for sync. Sync, by its nature, executes all the rules in the workspace file, and then if you write that down, you got the values. And it tells you, well, for build, you have another option where you say, actually, when building, ignore the workspace file, use that other file instead to know what the rules are. And then you can say, well, actually, use the hashes, verify the hashes of the external repositories. This is a file where you get all the hashes, and then you list all the rules where you want the hashes to be verified. For example, you might not want to verify that you get the same cc configure output. And actually, it looks a bit redundant to have the same file name there over and over again. But that can also be a feature. Remember, it's just a Starlark value in that file. So you can add another file that includes that value and that does some transformations to the recorded values. Like if you know, for my Git repository, I also have a way to download tar archives for specific snapshots. So all that transformation knowledge can go into a separate file. Okay, so that is the present. And for the future, we have some ideas. But more important, we want your feedback, what is needed and where we should go from there. So please talk to us either in person today or tomorrow or via email. Thanks.
Hello, everyone. My name is Chen. I'm from the Remote Execution Toolchains team from Canada. And today I'm going to introduce you a Bazel container. So a container image is a lightweight, standalone executable package of software that includes everything you need to run an application. And in this presentation, I might use the word container and image interchangeably, but for both, I mean a container image. And so the Bazel community has been asked for a Bazel container for a while, and our team builds containers for remote execution, and we are also the maintainers of Roost Docker and Roost Kubernetes. So we found ourselves in a position to provide a Bazel container as well. So we built it. So it allows people to try out Bazel very easy with no configuration or installation, just install Docker, and it's very good for CI as well. So the Bazel container is publicly available in the Google Cloud Marketplace, and you can pull the container at this container registry path. So here's what the landing page looks like, and the containers with different Bazel versions are kept available and pullable from these container tags. So in this container, we install it's based on a Google-maintained Ubuntu 16.04 base image, and we install a Google build and tested clan with sanitizer support. And in addition, we have OpenJDK 8 and 2 versions of Python installed to support Bazel's Java and Python builds. So there are several key features of this Bazel container. First, containers with different Bazel versions are kept available, and you can just pull them. You can choose which Bazel version you want. And in addition, to make building with sanitizers very easy, we have a default Bazel RC file in this container. So if you like to build with ASAN, TSAN, or MSAN, you just need one extra flag. So initially, when we come to build containers, we use Dockerfile, and we found ourselves copy-paste too much code. So to install the same tool or same compiler in multiple containers, we just copy-paste the same code in multiple Docker files. This is very error-prone and very inefficient. So we take advantage of Bazel and Starlark. So we developed a set of Starlark rules to construct Docker images using Bazel. So instead of specifying the files to add and the entry point or the command of the container, in Docker files, you specify them in Bazel build targets. And here are the rules, and they are in Bazel Toolchains repo, in Roost Docker, and also in base image Dockers. You can Google them afterwards, and these are all links as well. So here are 2 examples. So with these rules, it allows us to reuse and compose layer targets to construct complete images. So the toolchain container rule is, you can think of that as you create a complete image. And the language tool layer is an image that represents a very specific, only contains a specific tool or a group of tools. So in the language tool layer rule, you specify what packages to install and what environment variables to set for this layer and some other files to add. And in the toolchain container rule, you just specify a list of language tool layer targets in the toolchain container rule. So with this, you can easily create toolchain container targets by composing existing layer targets. So the one on the left is a simplified version of the Bazel container toolchain container targets, and the one on the right is just like a container full target, and they share the same Java and Python layer targets. But just to note that we are not reusing the actual layer contents or file yet. So if you first build a Bazel container on the left, then you build a container full on the right, you build a container from scratch. So in the coming quarter, we are planning to work on fully automating the release process and integrating it into the Bazel's own release process. And we are also working on making the container generation fully deterministic. And most importantly, we would like to make the actual layer contents reusable from cache, not just the targets. So that means if you build a the container full on the right in the previous slides, after you build in the Bazel container, then you will reuse the Java, clan, and Python layer files. And say, if you use multiple containers that share common layers in multiple cloud build steps on GCB, the Google Cloud Builder, then those common layers will just be pulled once and cached by GCB. So stay tuned and join the Bazel Discuss group at this link. And this container is also documented in the Bazel's website, so you can check that out later on this link. And that's it. Thank you.
Hi, everyone. My name is Jay. I work on the Go Tools language team here in New York. I'm the maintainer for Rules Go and Gazelle. And today I'm going to tell you about Autogazelle. So just a quick show of hands. How many people here use Go in any capacity? Cool, a lot of hands up. All right. Here we go. So Gazelle is a command line tool that generates build files for Go projects that follow traditional Go conventions. It also works for protocol buffers. So here's a build file that Gazelle generated for the Kubernetes project. Everything you see here is generated by Gazelle except for the lines in italics. Gazelle allows you to make manual changes to build files, and it'll preserve them after you run it. It'll update build files in place. You see Go library, Go binary here, bunch of dependencies. It works pretty well. Kubernetes uses this to manage over 2,600 build files. So in general, it's pretty successful, but coming from the Go ecosystem, people don't want to write build files at all. Generally, you can just like go build and go run, and it works, and why do I have to write this extra thing? And it's especially annoying that you have to run this extra command. You know, you do your editing, and then you run Bazel build, and it's like, oh, I forgot this dependency. It's not there. So I have to go back, and I have to run Gazelle, and now my build file works. So this is where Autogazelle takes over. This removes that extra step. So I have a quick demo for you. This is from the Kubernetes repository. And before I started, I deleted the Go rules out of all the build files. And I deleted this build file entirely from command kubelet. But we'll run a Bazel build anyway. See what happens. Autogazelle kicks off. It takes a few seconds to start up the first time. There it goes. It's all done. And we start a main build. It's in the cache already, so that finishes quickly. All right, our build succeeded. Let's see what's in the build file that Gazelle generated for us. All right, so we have our Go library and Go binary. This is the same build file as before. Because I deleted it, it doesn't have the manual changes. Let's make some changes of our own. So we'll open up kubelet.go, and we'll add a new import. Normally, this would be something that you have to update the build file for. We'll save that. And while we're at it, let's rename the file. I never could figure out how to pronounce it. Is it kubelet or kubelet? I'll just rename it to kubelet with 2 O's. We kick off our build. Autogazelle kicks off again. It runs a little faster this time. And we have to recompile and relink. This is a big binary, so it takes a few seconds. All right, there we go. Let's see what our build file looks like now. It looks like it picked up our new source file name and our new import. All right. Oop. My button's not working again. Can we go to the next slide if anyone has manual control? I'll just proceed. So how does that work? We have a bash script, and it's installed in tools/Bazel. And thank you. The Bazel that's in your path, when you run a Bazel command, is going to look for the script. And if it finds it, it's going to execute it instead of the real Bazel. So this script is going to run Autogazelle. And when it's done, it'll execute the real Bazel with your original command line arguments. So Autogazelle is a program with 2 pieces, a client and a server. And the client just connects to the server over Unix domain socket it uses for synchronization, doesn't actually exchange any messages. The server watches your file system for changes. And whenever it accepts a connection, it runs Gazelle in those specific directories that changed. So you get an incremental run. Gazelle runs much faster because it only runs in specific directories rather than the whole repo. So for a large repo like Kubernetes, that can save you several seconds. If you're curious to learn more, check out the Bazel repository. This is checked into command Autogazelle. And just a warning, this is like super new and experimental, so maybe don't quite use this for production projects yet, but feel free to try it out and file issues and let me know if you have any questions. Thank you.